Assalamualaikum. My name is Haziq. We are from Group 20. I would like to present about the numerical simulation of cavitating flow in liquid hydrogen through a convergent nozzle. So for the introduction, high speed fluid dynamics are essential in modern engineering, utilized in systems ranging from rocket engines to a cryogenic cooling. Convergent nozzles are the primary devices used to control these flows by converting pressure energy into a kinetic energy to accelerate the fluids. So this project focus on cryogenic liquids like liquid hydrogen, where a sudden pressure drop caused by cavitation. So the formation of vapor bubbles which significantly alter fluid's density and flow rates. Next, the objective of this project. The primary objective is to link fluid kinematic concepts. Then the project aims to model and stimulate the phenomenon of liquid hydrogen cavitation using a CFD. Then the study will analyze how changing the pressure difference between the nozzle, inlet and outlet affect the cavitation behavior. Finally, the researcher will examine the specific impact of altering the nozzle inlet diameter. Next, theoretical background. The analysis focus on two-phase flow, treating liquid hydrogen as a mixture of liquid and gas phases. The mixture density is calculated based on the combined volume fraction of liquid and vapor. The continuity equation is applied to ensure that mass is conserved as the fluid transition from a liquid to a gas phase. The momentum conservation equation is utilized to represent Newton's second law for fluids, tracking how pressure change and gravity and viscous force. Next, from the literature review, cavitation. As we know, cavitation is identified as a critical pressure drop phenomenon in aerospace application, where we managing system weight and speed is essential. So foundational analytical tools include the Rayleigh-Bézet equations, which remain central to understanding non-linear and transient bubble dynamics. Previous CFD studies have successfully explored cavitation in various geometries, including hydrofoils or orifices, and venturi nozzles. So most importantly, research emphasized the liquid hydrogen requires specialized numerical modeling to count for non-equilibrium and thermodynamic effects.
Now, I will explain the nozzle designs and how they affect the flow of liquid hydrogen. 3 convergent nozzle geometries were studied. First is baseline design, which has inlet diameter of 7.79 mm and exit throat of 1.02 mm. 2 additional designs were then created, one with 50% larger inlet and another one with 50% smaller inlet. The throat diameter remained the same for all the 3 designs, so only the effect of the geometry could be investigated. Changing the inlet diameter changes the flow area available for the liquid hydrogen. As the fluid passes the narrow throat, its velocity increases while the static pressure decreases. If the pressure drops below saturation pressure of liquid hydrogen, cavitation occurs. The simulation result shows that the 50% larger inlet produces a larger pressure region, resulting in larger vapor pocket. In contrast, the 50% smaller inlet limits the increase in velocity and maintains the higher pressure and reduced cavitation. Next, I will explain the simulation procedure used in this study. First, the nozzle geometry was imported into ANSYS workbench and 2D structured mesh was generated. The inlet, outlet and wall were then defined using name selections. Next, the simulation was set up in ANSYS Fluent. The mixture multi-phase model was selected together with the realizable K-epsilon turbulence model and enhanced wall treatment. 2 phases were defined, which are liquid hydrogen and hydrogen vapor, and the Schnur-Saw cavitation model was used to simulate the cavitation. For the boundary conditions, case 9 from the research paper was applied with the pressure inlet, initial pressure and also pressure outlet. The solution controls were adjusted to improve convergence and each simulation was initialized before running until the solution converged. After completing the baseline case, the simulation system was duplicated twice. The inlet geometry was replaced with the 50% reduced and the 50% increased nozzle designs, while all the other simulation settings remain unchanged. This ensured that only the inlet geometry was varied for comparison. Finally, the simulation results were imported into CFD posts for processing. 3 contour plots were generated for static pressure, velocity magnitude, and vapor volume fraction. In addition, the center line was created along the nozzle axis to extract pressure, velocity, and vapor volume fraction profiles for comparison between the 3 nozzle designs.
Explain about the result in this project. First is the residual convergence graph. This graph shows the scale residuals for the CFD simulation after changing the nozzle diameter. The residual represent the numerical errors of the governing equations, including continuity, velocity, energy, turbulence, and vapor volume fraction. Next is the velocity magnitude contour. For decreased diameter, the flow area becomes smaller. As a result, the liquids accelerate more rapidly. However, for the increased diameter, the flow area becomes larger, so the fluid does not need to accelerate that much. For the last part is the velocity magnitude versus position graph. For the decreased diameter, the velocity remains low at the inlet but increase very sharply as the fluid approach the nozzle throats. However, for the increased diameter, the velocity increases more gradually and reach the lowest maximum value because the larger flow area reduce the acceleration of the fluid. So to conclude everything, this project has successfully reproduced the CFD simulation of liquid hydrogen flow through a convergent nozzle based on the selected research paper. So from our simulation, we have observed the velocity increase significantly as the fluid passed through the converging section of the nozzle, while pressure decreased toward the outlet. So overall, all of the obtained simulation were very similar to the presented in the research paper, showing that our CFD model was able to reproduce the published results successfully.